In 1911, Ernest Rutherford proposed a model of the atom that followed the same gravitational logic as our solar system. Within the hydrogen atom, the simplest atomic structure, this model places a single proton at the center, with a lone electron revolving around it. However, the scale of this system is unlike anything in our macroscopic world. The electron's orbit is roughly 100,000 times larger than the nucleus it encircles. To visualize that distance, if the nucleus has a radius of 10 to the negative 15 meters, the electron's path stretches out to 10 to the negative 10 meters. This means that matter, at its most basic level, consists almost entirely of empty space. But this planetary model introduces a conflict with classical physics. A revolving electron is constantly accelerating, and according to electromagnetic theory, an accelerating charge must radiate energy, meaning it should eventually spiral inward and collide with the nucleus. To understand why atoms remain stable, we must look past the physical appearance of the orbit and calculate the mathematical forces that bind these particles across the void. The Rutherford model relies on the existence of a dynamically stable orbit. For an object to move in a circle rather than flying off in a straight line, it requires a centripetal force pulling it toward the center. In the hydrogen atom, this inward attraction is the electrostatic force between the positive proton and the negative electron. For the orbit to remain stable, the magnitude of this electrostatic attraction must perfectly equal the required centripetal force. This balance is defined by 4 variables: the charge of the electron, its mass, its velocity, and its orbital radius. If this precise balance fails, the electron either flies away or collapses, and the atom ceases to exist. We begin by expressing the electrostatic force using Coulomb's law, utilizing the charge of the electron and the vacuum permittivity constant, epsilon naught. We set this equal to the formula for centripetal force, mass times velocity squared, divided by the radius. Because the radius appears in the denominator of both sides, we can simplify the equation by canceling out one of the r terms. This isolation shows the relationship between the electron's velocity and its distance from the nucleus. This result establishes a strict interdependence between an electron's speed and its distance from the nucleus. If we define the radius of the orbit, the velocity required to maintain it is no longer a choice, it is a mathematical necessity. This force balance is the mathematical engine that defines the internal geometry of every hydrogen atom in the universe. Beyond the forces keeping the electron in place, we must also account for the energy it holds within that orbit. There are 2 components. First is kinetic energy, the energy of the electron's motion. By substituting our previous velocity equation, we find that kinetic energy equals E squared over 8 pi epsilon naught r. Since mass and the square of velocity are both positive, this kinetic energy must always be a positive value. The second component is the electrostatic potential energy, which describes the electron's position relative to the nucleus. Here, the calculation yields a negative value, negative E squared over 4 pi epsilon naught r. This negative sign is critical. It represents an attractive force, signifying that the electron is physically bound to the proton. The stability of the entire atom depends on the final sum of these opposing values, the positive energy of motion versus the negative energy of attraction. To find the total energy of the system, we simply add the kinetic and potential components together. The math reveals a specific proportion. The negative potential energy is exactly twice the magnitude of the positive kinetic energy. The resulting total energy of the electron is strictly negative. In physics, a negative total energy is the fundamental mathematical requirement for what we call a bound state. If this total were positive, the electron's energy would be enough to overcome the nucleus's pull, allowing it to fly away on an open path. It is this negative total that ensures matter remains cohesive, rather than dissolving into a cloud of free-floating particles. We can visualize this energy as a landscape, an energy well. The flat surface represents zero energy, where an electron is free from the nucleus. Because its energy is negative, the electron sits deep inside this funnel, unable to climb to the surface on its own. This matches experimental data. For a hydrogen atom in its lowest state, the electron sits 13.6 electron volts below that zero line. Ionization is the process of providing enough external energy to bridge that gap, lifting the electron out of the well and back to the surface. This is the core of the Rutherford atom, an energy trap, where the balance of forces keeps the electron in motion, but the deficit of total energy ensures it remains captured.